Hello students, welcome to the sixth lecture of linear algebra. Today's topic is going to be Schur's complements. Okay, so we introduced this in the last class itself, so let's very quickly do a review of what we discussed and we'll continue from there. Right? So Schur's complement has to do primarily with block matrices. So let's say we have block matrix of this type A, B, C, D. We'll call this overall block matrix as M. Okay, so this overall block matrix is going to be a square matrix, and typically we'll assume A and D also are square matrices. So A is n cross n, D is m cross m. They could be potentially different size square matrices. That fixes the sizes of B and C because of the block structure. B is n cross m and C is m cross n. Okay, so now considering this block matrix structure, Schur complements give a very important tool to understand the properties of the overall matrix M in terms of the smaller matrix A. Okay, so we defined the Schur complement of A in the last class to be this matrix D minus C A inverse B. Okay, as I told you, one way to easily understand this is assume you are starting. Suppose if you want to find the Schur complement of A, you start from the matrix that's diagonally opposite to A, that's D, and go around clockwise in the matrix. Okay, so D minus C A inverse B. Okay, and we can easily make sure that these products actually make sense. So C is m cross n, A inverse is going to be n cross n, and B is n cross m. So this product will actually work out to be, so this product will actually work out. It's going to be compatible matrix multiplication. Okay, so this overall matrix is, by the way, m cross n. Okay, this is the Schur complement of A in M. Sometimes it's written like this, M by A. We'll see the reasons for this notation in a minute, but this is written like this. The Schur complement of A, the Schur complement of A in M. Okay, that's how you would read it. M by A is the Schur complement of A in M. Okay, that's defined like this. In the last lecture, you might recall that we defined it for symmetric matrices. So in the last lecture, instead of having C here, we actually had B transpose. Okay, so if M is symmetric, then C is equal to B transpose. Okay, because of symmetry, and you also will have A and D also will be symmetric. Okay, A and D are also symmetric. Correct, if M is symmetric. So this is the scenario that we were discussing in the last lecture. Okay, in the last lecture we were focusing on the case when M is symmetric, and we had the following important result. We said that M is positive definite if and only if, this goes both ways, if and only if both A and the Schur complement of A, that is M by A, are positive definite. Okay, it's an extremely powerful and very useful result. Okay, so this says two things. It says that if I want to prove, for example, that M is positive semi-definite, so overall matrix is positive semi-definite, I can simply choose to prove that A is positive semi-definite and the Schur complement of A, that is this one, is also positive semi-definite, positive definite. And if I do that, the overall matrix M becomes positive definite. Okay. Conversely, it also says that if M is known to be positive definite, then automatically both A and the Schur complement of A, are positive definite. Okay, so it's an if and only statement. This is the main thing that we proved in the last lecture towards the end. Okay, a minor modification of this is also possible. You can actually say that you can also say a similar thing for positive semi-definite matrices, right? So for example, you may be very tempted to say this if and only if A greater than or equal to 0 and M by A greater than or equal to 0. This is more or less true, but you have to be very careful here. The main issue here is that M by A, the definition of M by A involves taking the inverse of the matrix A, correct? And if you allow A to be positive semi-definite, it means you are allowing A to be non-invertible. Remember from one of our previous lectures, we said that positive semi-definite matrix can also be non-invertible. So if we allow A to be non-invertible, then how do you actually take the inverse of A, right? It's not really well defined here. Okay, so for that reason, this statement only makes sense if A is allowed to be invertible, meaning that A should be positive definite, not positive semi-definite. Okay, so this is how you restate this. Okay, you say that M is positive semi-definite and A invertible if and only if A is positive definite and M by A is positive semi-definite. Okay. So in other words, what this is trying to say is, if I want to make sure, if I want to check that the overall matrix is positive semi-definite, all I need to do is pick a block matrix A here that is invertible. Okay. Make sure you pick an invertible one. Then I need to check that the invertible block that you picked is positive definite and the Schur complement of that is positive semi-definite. That ensures that the overall matrix is also positive semi-definite. Okay. So it's a very powerful tool, and if there is a takeaway, I assume these are the main takeaways. In this lecture, we'll try to explore a bit more on Schur complements and try to understand the reason why they actually turn up. Why do you have an expression like this in the first place? Okay, fine. By the way, just a quick note. In the last lecture, we were discussing for symmetric matrices, and it's important to note that when we talk about positive definiteness and positive semi-definiteness, we implicitly or inherently force some sort of symmetry. Okay, we assume a symmetric matrix. But as I said, today you can actually work on any general matrix. It doesn't have to be symmetric, and even then you can define the Schur complement in this way. Also, what if, for example, these two terms B and C are 0, right? In the Schur complement, if B and C are 0, then what happens to this expression, right? If B and C are 0, then this is nothing, right? This becomes 0. The Schur complement of A is simply D, right? Schur complement of A will just be D. Okay. So these special block matrices in which the so to speak the off diagonal blocks are 0 are called block diagonal matrices. Okay. Let's just write it down. Block diagonal matrices. Block diagonal matrix is a matrix of the form A0, 0D. Okay, it looks like a diagonal matrix, but it's actually block diagonal in the sense that this is actually a large square matrix. This is also another large square matrix. Okay, for any block diagonal matrix, the Schur complement of A is actually just D. It's simply the matrix that is diagonally opposite to A. Okay. By the way, you can also define very similarly the Schur complement of D as well. Okay. So for example, you can talk about the Schur complement of D as, right? If you want to find the Schur complement of the very same way, what you will do is you will start with A, right? The matrix that's diagonally opposite to D, and run clockwise. Okay. So that will actually give you A minus B D inverse C. Okay. In order to be able to define the Schur complement of A, you need A to be invertible. In order to define the Schur complement of D, you need D to be invertible. Okay. Right. So in that vein, if A is invertible, then the Schur complement of A can simply be defined as D, and the Schur complement of D can be defined as A for a block diagonal case. Okay. So in fact, a similar thing will work even if you have block triangular. Okay, meaning that you have A, 0, C, D, something like this, right? So here B is 0, meaning that if you actually look at this matrix, it reads like it looks like a lower triangular matrix in sense upper triangular entries are 0. Even in this case, you can easily see that the Schur complement of A is D. Okay, and the Schur complement of D is A. Okay, right. So we will actually be looking to these as our special test cases to understand Schur complements better. Okay, fine. So let us actually see why Schur complements arise. Okay, we saw one context in which they arose naturally was when we were trying to partially minimize quadratic forms. Okay, partially minimize quadratic forms. If you recall from the last lecture, the reason why we got Schur complements was that we were fixing one set of variables and we were allowing the other set of variables to vary. Okay, and minimizing on the other set of variables while keeping one set fixed. Okay, so this idea of, in some sense, fixing some variables and allowing some of the other variables to vary, okay, is what gave us Schur complements. In general, Schur complements arise due to the process of eliminating some variables. Okay, eliminating variables. So now suppose, I'll explain this in detail now, right? So suppose you have a system of equations of the form mx equal to b. Okay, so you have a system of equations like this, mx equal to b. Okay, so M is like a square matrix. Okay, let's assume M is a square matrix. So M is of size n plus m cross n plus m, like in this the beginning of this lecture, and B is an n plus m cross 1 vector. Okay, and X is a vector of unknowns. X is probably a very large vector. I want to solve the system of equations, but I am not interested in finding all the coordinates of X. Okay, so suppose I am only interested in finding a few coordinates of X. Okay, so only interested in finding the first n coordinates of X. Okay, just as an example, right? So I'm only interested in finding the first n coordinates of X. So suppose your X is partitioned like this, right? So X is partitioned as x1, x2. Okay, but this is the first n coordinate, so it's n cross 1, and this is m cross 1. Okay? I'm only interested in finding x1. I don't care about x2. Okay, and this is very common, right? When you're dealing with a large system, maybe the variables in x2 are like hidden variables or variables that I do not have any control on, or simply I'm not interested in them, right? I only want to find x1. Okay, so what do we do, right? So the natural process is to eliminate x2. Okay, and how do you eliminate x2? The first step is to actually partition x like this, right? Once you partition x in this way, let's actually rewrite this system of equations over here as a block form. Okay, so you have partitioned your x. So this is supposed to be your overall matrix M. You have partitioned your x into x1, x2, right? And similarly, let's partition my b into b1, b2. Okay, where b1 is the first n coordinates, b2 is the next m coordinates. Okay, so I have partitioned it like this. Now, naturally, this partitioning also induces a partitioning on the block matrix here. So A, B, C, D. Okay, this also partitions the corresponding block matrix A, B, C, D. Okay, we'll continue in the next portion of this lecture.